Okay. Yeah, hello everybody. My name is Konrad, here to talk to you about Swift and Java. So there's going to be a lot of Java code here. Please brace for that. So Swift, of course, you know everything about open source and cross-platform, and I really want to lean into the cross-platform aspect. So we do care about use cases on Linux, embedded, and of course our own platforms, but a lot of this talk will be actually about server use cases. So of course, it's memory safe and concurrency safe, and it's a natively compiled language, unlike Java. Swift, since day one, had native interoperabilities with C, and recently we added C++. And now we're really trying to interoperate with a non-native, so a managed runtime, Java. So why do we even care, right? Why would we invest in this interop at all? So we care about memory safety, and we think Swift is a fantastic language to write your native code with. Now, some Java applications end up having to use native code, and when they do that, they usually resolve and use C. We think that's not a great idea. Instead, you should be using Java with Swift, a memory-safe language, instead of going back and using C. We are great at incremental adoption stories as well, so this is a great use case for that. And there's another aspect, which is code sharing. When you have an app and you have some shared code that maybe a server-side application also would like to use, we would like to make it easy, even for Java server-side services, to use that shared Swift code. So where do we care about this? Primarily, I'm currently working on Java services use cases. So new and exciting Swift libraries that people like to use from their Java services. But also on Android, where this shared core library might be quite interesting. There's two directions to this interop. Primarily, a Swift application trying to call into some existing Java library, or a primarily Java application calling into an existing Swift library. You can see it's kind of an inverse story, and the use cases are very different. But it's part of the same interoperability story. So there's another big difference. So historically, there's one API available to Java to call into native code, and that is the Java native interface. That has been introduced in 1997, so a very, very long time ago. So it has a bunch of limitations, and it's not that nice to use. But it is still the very much de facto standard of how you interop with native code in Java. There's a new API as well. It's called the Foreign Function and Memory API, and this is actually what I will be talking about today, because it's much more modern and flexible, and we can do new and exciting things with this new API. That has been introduced in Java 22, and that was in 2024, although it's not in a stable LTS release yet. So it will be actually stable in Java 25. So Java and Swift kind of feel very different, right? But they're actually very similar on a high level, at least. Java is all about classes and primitives, although it doesn't have the rich value types that we have. They're actually working on adding things like our structs, right? So there's increasing overlap between the two languages, except for runtimes, right? The runtimes differ because Java is garbage collected with a garbage collector, where Swift is managed using an automatic reference counting system, at least for the reference types. So generics also differ, but the general idea of generics and how a developer interacts with them is very much the same. So in Java, they're erased at runtime. In Swift, they're not, but the general idea is really the same. And there's other differences, like exceptions in Java are really exceptions with stack traces, while they're values in Swift. And of course, the threading system is slightly different as well. But you can see we're really solving similar problems and arriving at slightly different solutions to them. So really, bridging should be possible. Before we jump into the foreign memory APIs, I would like to show you the other direction. So using this code called JavaKit. JavaKit is a Swift library and set of Swift macros that you can use to call into Java code from Swift. Again, I should preface all of that. This is very much early development. Everything here will change. None of these APIs are stable. None of these names are stable. So please treat this as a preview, right? So here you can see we have a Java type. It's called CFR, and it has a method called find primes, right? So it will give you prime numbers in a Java list, and they're Java integers. You can actually inform the Swift Java project by providing a configuration file which points at the jar, so the class path, where to find this class, and give it a name, because we have to disambiguate names sometimes because we don't have deep packages like Java has. Given such a config file, we have a Swift PM plugin that will generate this wrapper class for you. So you can see it's a Swift type, it's a class. It has annotations on it, so Swift macros for the Java class, the Java method, and there's the Java static method for the find primes. And it basically mirrors the signatures you've seen in Java. Now, all you need to do to call into this Java code is get a JVM. The Java needs a JVM to run in. You can instantiate that from the Swift application, and you can immediately get the Java class and literally call the method on it directly. And you can see we're even able to iterate over it, right? Receive class, find primes. This is a Java list we're iterating over here, right? So the interop is already pretty cool here. So the rest of the talk I want to spend on the other direction. So Java calling Swift, primarily because this is where I spend most of my time currently. And this is also very exciting because it's new APIs, and we can show you how we can very deeply integrate the two languages. So the build usually looks something like that. You have an app, and it has some Swift sources, and it would also have some Java sources, probably. While Swift C compiles the Swift sources, we can use Java C to compile the classes. In order to have Java have access to the Swift code, we will create a dynamic library out of these Swift sources, right? So this will be a dylib, an SO file on Linux. Next up, we will use the tool called jextract Swift. Again, names may change, but we will use a source generator in order to analyze the Swift code and provide Java with the necessary wrappers, so Java code, in order to call down into the native Swift functions. We will also generate a little bit of Swift code that is necessary to glue the two worlds, right, the two ecosystems. We then build this all into this dynamic library. We can include the dynamic library and classes into a jar, so the distribution unit of a Java application. And this is how a Java developer might use our app. They may not even know that we have been using Swift to implement it. Our library, I should say. So, a brief command line example of how this looks today. So you can use jextract Swift on an existing source directory. And what it does is, firstly, it has to analyze the Swift code inside that module. So we do some analysis, we figure out what methods it has, what types, and then we have two source generation steps. One is to generate the Java types necessary for Java to call into Swift. Today we use the foreign memory APIs, but we could also generate JNI-based APIs for platforms which do not have the foreign memory APIs. And we generate a little bit of Swift code as well. So, for example, this is how we would import or extract a public class, my Swift class. It's a class, so in Java it shows up, again, as a class. It implements the Swift heap object, which indicates to us that this object will be reference counted. It's a Swift heap object. And the memory segment here is basically a pointer to native memory where this object lives. If we import or extract a Swift struct, it looks pretty much the same in Java because Java doesn't have structs, right? We have to represent it as a class. However, we implement the Swift value interface. The Swift value interface means we have to copy around this value as we modify it. It's a value type. Methods and initializers get imported the same way. So they kind of mirror the signatures you have on the Swift side with small modifications to the types, right? So a int on the Swift side becomes a long on the Java side, yes. Right? Because int 64-bit, depending on platform, in this case, it's a long. Okay. So, okay, we can do this with sources, but sometimes you don't have access to the sources of a Swift library. For example, if it is provided by the operating system. But in that case, we actually have Swift interface files. And we can use the same tooling to extract the interfaces from the interface files, because all we really need is the types and the signatures. We don't need the method bodies. So even for a library provided or a framework provided by the OS, we would be able to call down into it and generate the necessary wrappers. So let's dive into some actual code. How do we do that? The first one I would like to discuss is initializers. We have some very interesting properties, and we'll use it to explain how Swift works. So here we have a Swift class. Let's use a class first as a simple example. And below, brace yourself, there's going to be a lot of Java code that I will now be explaining. So using these new APIs, we can explain to Java that we will be calling a native function, and the signature of that native function is such that it returns a pointer, right? It returns the object it initialized. It takes an integer, it takes a pointer, which is the capacity object here, and it also takes another pointer. What is that? That is the type metadata. So initializers in Swift actually provided a type metadata of the type we're trying to initialize. And we have to find an instance of that type in order for Swift to be able to, call this Swift function. How do we do that, though? Like, Java doesn't know about Swift types. So we can do something. So we're basically looking for the dot type of the type we're trying to create. We can use a trick and actually ask Swift, so call down to Swift using a foreign function API call down into Swift, and then implement this using a Swift function that literally just spells out the type in Swift, but we return it as a mutable pointer. Well, just as a raw pointer, really. Java doesn't really know what that means. It knows I have a pointer to the type, and now we can provide it into that initializer we talked about, right? We got the type metadata, we get the pointer to it, and now we're able to call the initializer directly from Java. This is really cool. We got an instance created by calling it directly from Java. We initialized a Swift type. Okay, so that was a class. Do you think structs are any different? They are. They're actually much different than that, because structs, as you know, can be allocated on the stack or in the caller, basically. So the way structs are created is we not only have to provide the type, of course, we have to provide a place into which that struct will be initialized. Okay, great, but that means we have to allocate some memory, right? Arena allocate, but I don't know how much memory to allocate, right? It depends on the size of the type. So we need to figure out how big is that struct. So what is the size of a struct in Swift? We can actually try to calculate that and see, okay, here's an integer, here's another integer, those are 8 bytes. Then there's an object, there's a pointer, I know that's 8 bytes. And then there's another struct, and we can descend and do the math and calculate the size of the struct. You can do it by hand. Or you can do it with Swift. In Swift, you can say memory layout, give it a type, and get the size of that type, and Swift will give you the correct size of the type. So that's really cool, but it doesn't actually work for generic types. I cannot manually calculate that, right? If I have a my Swift struct, and it's generic over object and value, right, var object, I don't know the size of object. I don't know the size of value. So as a source generator, which we're effectively building, I cannot answer these questions because the exact size of the mySwift struct depends on the exact types provided to it. And this is only known at runtime, right? If I say mySwift struct int, it's 32 bytes. But if I say int string, it's suddenly 40. So how can we teach Java to do that? Oh, and of course, why is this important? Because Swift is able to allocate dense arrays and dense pieces of memory using this information, right? This is how we can create arrays of structs and their densely packed memory. This is actually super cool and something the JVM cannot do. This is impossible to do on the JVM for user-defined custom types. So this is really cool, but how do we solve that? We can solve it because we have the type. And as you may have guessed, the type has some way of knowing that information. We can go to the so-called value witness table from a type. We can do some pointer arithmetic, figure that out. And now we have a Swift value witness table. A Swift value witness table is something that is a structure in memory that contains pointers to functions, such as assign with copy, assign with take, so for moving memory around, destroying it, but also it has the size and the stride of that object. And the size is exactly what we need to find here. So, this is very exciting because we can use the foreign memory API in Java to explain to Java that, hey, there's this struct in memory, it has this exact layout, and there's these exact fields in memory. If I give you a pointer to it, at this and this offset, there will be this and this field. So we can explain to Java, here's the layout, here's the size. Now I can access the size for any type that I already have, and for example, I can find out then the size of any type that I found in the previous steps. Now we can write a function that creates a memory layout based on a Swift type metadata. We have to do a little bit of math and adjust for padding, but basically we're able to explain to Java exactly the memory layout of our Swift objects. We can even name them, but that's for debugging at the bottom there. So what we just did is explain to Java that this struct will have whatever amount of bytes, but Java doesn't really understand the details of that, right? It's just a piece of memory. We could actually do further than that, go further than that, and explain to Java that at these exact layer offsets are these exact fields, as we just did for that struct, right? So we could do that. We don't do that today. It's a bit more complicated for Swift structs, but it's something we could do using this API. Why would we do that? Because we would have direct memory access to fields without having to do native function calls, which is much, much faster. So this is very exciting future work we could maybe do. So in order to check if we did it all right, we can see that now we have a layout for a specific type, and we can allocate memory using it. So you can say arena allocate a memory for that exact type. As you can see, the returned layouts here have the exact correct size as you would expect. So 8 bytes here, 32 here. So let's call about member methods. So invoking members is actually the thing we want to do, right? We want to call methods in Swift types because this is where the interesting logic lives. So we have a method here that's called capacity. It returns a struct. So what do we have to do in order to call it? Again, I'm explaining to Java, this will have a self-pointer, and because the returned value is a struct, it will again be returned indirectly. The same thing we talked about with initializers. And I should be able to just call that, right? I call it, I do the down call, and as I get the pointer back, I wrap it in another wrapper for the capacity struct. There is a little bit of trickery though, and we have to provide Java something to call. So this is a so-called func. We use a C declaration calling convention because Java only knows how to call C functions, really. So we express a small bridge between Java land and the underlying Swift native code, and we just do some type conversions there. That then makes a call into the actual Swift function using the Swift calling convention. Now, in an ideal world, I wouldn't have to do that. It would be lovely to call directly from Java into the struct, but we cannot do that. So why is that? We cannot do that because the self, among a few other things, is passed as a register. And the calling convention is different, and Java just wouldn't be able to call this function natively. Swift is ABI stable, at least on Apple platforms today, so we actually even know exactly which register is passed in. So it's in this one here on x86 and on x20 on ARM. So we know exactly what to do. So in theory, we could go in and teach the JVM to do a Swift calling convention if we wanted to. That's a future experiment we could maybe get to, but you see, this is why we have to do the funking, right? This intermediate step of going through a C calling convention, because the JVM does a C calling convention style call. Lastly, I will quickly talk about lifetimes. So as we created objects, we called things on objects, we also have to destroy objects. So in Swift, destroying objects is very predictable, right? Let's look at the bottom example here. I have a container, I created it, it has a person inside of it, and then I assign nil, right? So this should destroy this container value. What does destroying a value actually mean? If you think about it, it really is exactly getting the value witness table and then calling this destroy function that is stored in this witness table. That destroy then, because it knows what exactly is contained inside that type, figures out it can destroy the number, it can destroy the person. Destroying a person means reducing its reference count, and if the reference count is 0, it means we have to run the dinit of that person. Right? So deinitializers are triggered indirectly through this destroy. So how do we do that with the Java wrappers, right? When we stop referring to objects and want to destroy them in native memory. We actually have a type called a Swift arena, and not only can it allocate memory, it can also register and destroy objects. So as we create objects, we can register them, and then using a typical in Java pattern, which is a try with resources. So this is a Java syntax here, try with resource. And at the end of this scope, this object will be destroyed. And because it gets called close on, we can destroy all the structs that were created during this scope. So we have predictable memory management, even though Java technically is, GC language, right? But using this pattern, we can have predictable exact memory management. The same is for value reference types. Next up, guarding against programmer errors, we can protect you from making mistakes. We can protect you from calling methods on memory which has been deallocated, right? Very important. We want to retain memory safety. And we can actually also rely on the garbage collector. We can use a Swift arena of auto. So auto means garbage collected, basically. And you can use this arena to create your Swift objects, and it will basically use the garbage collector to eventually call destroy on these objects. This is a bit unpredictable, right? The GC is unpredictable when it will do that, but eventually it will. So as you can see, this is a very deep integration. We're not only making a few method calls, we're really deeply explaining to both sides how the memory layout of each looks like. And it's memory safe all the way. We protect you from making unsafe calls. It's very nice to use. Of course, we today talked about the internals of that, but using it, you just call methods and things kind of look like you would expect. So Java and Swift can work great together. This is ongoing work, so please join us in building this project. It's open source, available on GitHub, and I'm more than happy to work with everybody on it. Future challenges include a JNI mode, which would be, for example, available on platforms where these new APIs don't exist. Integrating with build tools, right, to make this much easier to work with, whatever your build system might be. And performance generics, and more, covering more of the language we want to interop on. So, arigatou gozaimasu. Thank you very much, and please join us on the forums and GitHub. Thank you.